Hello friends, here we are again to examine the operation of ferrites in applications useful for amateur radio and maker spaces, and this is in EMI suppression. Now in ham radio sense of EMI, we are our own EMI. That is, there's an antenna that's inducing currents into common mode currents into the transmission line, be that twin lead or coaxial cable. Now I'm going to return to some familiar graphics here, and this represents the transmission line, be it twin lead or coax, matters little, as long as the entire circuit fits within the open space of this core. In other words, these two lines are continuous to this load. So they're hidden as they go through the core. This source sees this load and nothing else. The core, as I mentioned in an earlier episode, this core has a bulk resistivity to common mode currents, but we haven't any common mode in this representation. This does represent the operation of common mode suppression, but it's done by forcing the loop going through and around and back with just one lead in the interior of this core. When this happens, this turns on the resistivity of the bulk resistivity of this material, and it imposes or inserts, if you will, a resistor into this circuit, which is lossy. It's true loss. It's resistive. It's inductive, capacitive as well. And those impedances add up to a suppressed current in this circuit here. Now, what's that have to do with this? Well, we don't have a common mode circuit here because we don't have a third plane of conductivity. Unfortunately, coaxial cables do, and as I mentioned before, this is a crude representation of a coaxial cable, and it's fine as it goes, but the shield of the coax is actually has two surfaces. The inner surface, which is paired with the inner conductor, which is represented by this figure, and then there's the outer surface of the shield, which is electrically, and yes, it's a piece of metal. Both sides are certainly conductive through them. However, the at RF levels, the penetration of currents into metal is not very deep. And as such, the interior of the shield is principally an insulator. Insulator in the sense that there's no current flowing in it by virtue of what's in the other lead. In this case, the other lead is the center conductor. Now, the outer surface of the coax, is a separate circuit, but it's fed by when the power from the transmitter back there arrives at the antenna, it has to split out. We're thinking of a dipole, a fan dipole in this sense. And when that drive point, the extension of the transmitter there, is up at the antenna, it sees each of the dipole elements and the outer side of that transmission line going back to the transmitter. That is the common mode path, and this is what we see in this representation, where this loss we can see because there's a current going through it, penetrating once, so to speak. And this, our former transmission line, now seeing two sources of resistance in each lead, but by virtue of this path here, which is identical to this path right here, except this generator is now found down here. And this generator represents our transmitter trying to impart all of its power to this resistive load out here, the dipole antenna or monopole as the case may be. And the induced current into this transmission line trying to go back, complete the circuit this way, sees these resistive elements. Now, if we step forward in this progression, we'll see that on the left side here, we have, this is not expressed in terms of coaxial cables or transmission lines. This is just a simple loop of wire going through that donut, that core, in one loop, and it exhibits this resistance, this ohmage, this impedance. Most of it is resistive, some of it is reactive. However, if we look at 10 megahertz here, we'll see that with one loop of wire going through the core, it will present about 100 ohms of resistance. In other words, the bulk resistance of these two resistors is going to be 100 ohms. However, if we pass the wire through twice, we can see that it's going to appear to be about 500 ohms of resistance. And if we pass that wire through 3 times, it's 1200 ohms of resistance. So we've gone from, what is it, about, well, we've gone through this progression, and this progression informs us on the applications for balance, in that if you can take your transmission line and wrap it through the core center of each loop, will, by the square of the number of loops, increase the impedance of the core. The core is going to see, well, for 3 turns, 9 times as much impedance. So if the core was for 1 turn rated at 50 ohms, well, now it's going to be 450 ohms with just 3 turns through. Now this is far and away distinctly different from turns ratios in the magnetic coupling of power transformers. These are at way lower frequencies. And if you were to try to run those cores at RF frequencies, then we would encounter, well, these resistances, of course. And well, what does that mean? Well, I guess I'm out of sequence here. It means that things get hot. And this is from Ferrites. You can see the manufacturer's name right down here, Ferrites 67 material. And you can see that we have a heat map. And Ferrite is proclaiming that its cores have less loss. This is a heat map. This is, things are getting hot, 34 degrees Celsius. Their competition would get up to 63 degrees Celsius. That's we can start boiling water on this one soon. And that was at 10 megahertz as they specify. So these things, they truly get hot. This material, like I say, truly gets hot. It'll burn you if you can get enough. If you can arrange for something to drive that high impedance, mostly resistance, it's going to heat. Now, and if we go through that core, 1, 2, 3, multiple times. There's a limit. There's a practical limit to these things. 3 is certainly one of them. 5, I would, let's just say that 3 is monumental, because the typical applications of these cores are in very tight-fitting scenes where the core itself its inner diameter is roughly equal to the outer diameter of a coax with its plastic sheath. So you're not going to get a second turn through that core, much less 3, and we're not going to even go to 4, 5, and beyond. So returning to the application here, we can see that, yes, this is truly resistive, and it's by virtue of a loop going around it. Now, here we have, we're getting into the intermediate complexity of the features of the ferrite resistances, bulk resistivities by various lot numbers or production numbers. We have a cross frequency here, impedances of the material along here, 0 to 500 ohms. We have a 75 material, a 31 material, the 61 material, a 43 material, and a 46 material. And the bulk of them, especially in this region, all have similar properties. And if we look at that, it's between 10 and 100 megahertz. So many of our own bands lie in this region, so these particular formulas, that's what they're called by Ferrite, formula 31, 43, 61, 46, any of these are going to present, let's say, at 20 meters, somewhere between 100 ohms and 200 ohms in this form. So it's these are by millimeters, so that's about half an inch by a quarter inch by 1 inch in length. So it's a small core. Inner diameter is 6 millimeters. So let's see, that's about a quarter inch. That's roughly the size of an RG58 cable, I would suspect. And 1 inch, that's pretty long. That's a long core for that size. So we have a lot of resistance here. Well, if we wanted to double this, we just add another core on that cable. We want to triple it, well, we add 3 cores to that cable. It says that it is as simple as that. You can bulk up the isolation of the transmitter here from the antenna. In other words, the isolation is it's expressed in terms of the common mode resistivity, and we can build that up, stack it up just by adding these cores over a length of RG58. And I've built balance in this regard. About a dozen beads in this stretch, giving me about 600 ohms of isolation from this end to this end across all HF. Yes, so it's very simple to achieve, and we have what's called a choke or a 1-to-1 balun. It can be an un-un balun or bal-bal. It all depends on where you connect Earth, because we still have Earth behind us, and it's always present, and this is why we're using these. Now, the approximation of this circuit found historically is it's just looping your antenna lead near up here at the feed point. And that loop, that coil, 8-inch coil of about 8 to a dozen turns, presents about a k-ohm of isolation. Now that will raise other issues of how the currents got into the transmission line, and I'll cover that in the advanced topics. This is just the intermediate. So let's see if I've covered all my material here. Go back to it. Yes. That's just the various materials. You know, that's the end of the that presentation. Returning, there's an example of just one core. And let me expand this so that you can see this and how it's. Let's see. This is a type 64, I believe, and it has a peak here at about, let's see, that's 2 megahertz, and then it starts to fall off. Now this black line is the impedance, and you can see that the red line that is hugging it so closely is the resistive element of this impedance, where when we get down into this region where the resistance separates from the Z, it's by virtue of the reactance that is presented by the core material. So this is a frequency plot of the common mode rejection for one core, this part number, and yes, let's just return to the hand check here. If you go to Ferrite, they're going to have, I think their catalog is 700 pages, most of them like that last graphic, showing a particular response curves that will be interesting to the designer. Now, our applications of Ferrite materials are somewhat outside of what was principally their core core competency, that sense, in building ferrite cores for power conversion. This all is way down in the lower frequencies, not up in the HF where as this slope shows, where the resistance just climbs like a meteor. Well, I guess that's an inverted metaphor, but there we are. So using inverted metaphors, I think, proclaims that I should extend my 73s here, and we'll talk about this next in later episodes. So goodbye, all.